Okay, so let's look today at some properties of functions. And that's going to be some old and some new properties of functions and some old and some new functions that we're going to work with. First of all, a base or a parent function is the simplest form of a certain kind of function. It will have the defining characteristics of that type of function, but it won't have any transformations applied to that. So our go-to example of a function that you have seen before would be something like a linear function, right? Your linear base function is y equals x. There are other linear functions, but some of those will have transformations. The base function, the parent function for a linear function is y equals x. Now, before we really get going here, we are going to jump right to the handout. We'll go through a few things here. I'm not going to go through every single step with you here in the video, but I will get you moving so you would be able to follow along if you so chose. So first off, we're using Desmos. You can find that, just Google Desmos graphing calculator and it'll come up to you. And we're going to sketch the first four functions on our handout. Now the first four functions on our handout are the linear function, the quadratic, the cubic, and the radical. So what you are expected to do would be to jump into here and you can just type in the equation. The graphing calculator will spit out the sketch that you're supposed to work with. Many of these ones you have seen before. So your linear function, you've been working with that since grade 9. Your quadratic function, you've been working with this since grade 10. Then we have our cubic function, which you should have touched on in grade 11. That's the one showing up in green here. Let's show only that for you. And our radical function here in purple, where the radical function is one arm of the inverse of your quadratic function. So you should be able to use Desmos to come up with just rough sketches here of your linear, quadratic, cubic, and radical to piece together what we're going to be working with in here. Now from there, what we want to do is take a look at our domain and range. We worked with our domain and range earlier this week, so we should have those skills here. We'd like to state the domain and ranges of each of these functions using our set notation that we were practicing yesterday. So our domains that we're working with, in each of the first three cases, our domains are all x is an element of the reals. What I would like you to do, you should have the skills to handle problems like this, so just pause the video here, try it out on your own, and compare your work to these 8 answers here. Once you've finished that, then I would like you to try that same thing out with x-intercepts and y-intercepts. You should be able to rely on your grade 11 knowledge and skills along with the sketches up here to find the x and y-intercepts there. And once you're finished that, then we go back to our note for a few more definitions that can push us forward. So we're finished all the first 3 parts of this activity. Now we're jumping into definitions. So an asymptote. An asymptote is a line that a function or relation approaches but never reaches. It will get infinitely close, so it can get as close as you want, but it will not touch the actual line that is the asymptote, at least on some part of its domain. Now, asymptotes on a graph are represented by a dashed line. A dashed line. Now, a continuous function. A continuous function is a function that does not contain any holes or breaks. Any holes or breaks on its entire domain. So a hole would be something like if we had a function here that looks like this. There might be a hole somewhere along the function or relation. In this case, it's a function. There might be a hole somewhere along where the function does not exist right there. We're not going to focus too much in this course just yet on why a hole might come to play. We'll see that in a couple weeks. All we need to care about is that there is a possibility of a function where it does not exist at a certain point. If it does not exist at that certain point, then we say there's a hole there. If there's a hole, it means the function or relation is not continuous. Otherwise, we could have a break. An example of this would be like our reciprocal function, 1 over x, which has a break in between, a break at x equals 0. And I can check that out if I'm sketching this function, and rather I'll do it nice and slowly for us. If I'm sketching this function from left to right, it sketches nice and smoothly, and then I need to let go. I need to lift my pen off of the paper, bring it all the way up to the top, and keep drawing. Since I had to lift it off and move it, then we say we have a break. Now, this function itself, the reciprocal function, would actually have a couple of asymptotes. It would have a vertical asymptote right here at x equals 0. We'll label that x equals 0. And it has a horizontal asymptote as well at y equals 0. And that means that in each case, our function, the reciprocal function, is getting closer and closer to each of these asymptotes, but it will never reach them as either x approaches extremely large values or extremely small values, or as x approaches 0 from the left or from the right. Now, a continuous function can be drawn in one stroke without removing your pencil from the paper. So that is how we're going to remember, how we're going to be able to tell if a function is continuous. Right here, if there's a hole, we see we would have to lift up our pencil from the paper right where the hole is, thus making it not continuous. And over here with the break, as I showed before, we need to lift our pencil from the paper and then move it considerably in order to keep drawing. Now, a function can be continuous on its domain. An example of that would be, say, a radical function. A radical function, its domain is x is an element of the reals such that x is greater than or equal to 0. Now, this is continuous along its domain. If I'm only drawing this function from x equals 0 and to the right here, then I never lift my pen up from the page, and it is continuous here. So it's continuous on its domain. Now, another kind of a function is continuous everywhere. An example of that would be like our base quadratic function, which we can draw the entire thing on its domain smoothly without lifting our pencil from the paper, but also its domain is the entire real numbers. And since its domain is the entire real numbers, it's continuous everywhere. So continuous everywhere functions are also continuous on their domain. It's just that their domain, the difference is their domain is the entire real number system. Now, if a function is not continuous on its domain or continuous everywhere, then we say it's discontinuous. Now, a discontinuous function then is a function that does contain a hole or break. And this hole or break we call a discontinuity. Oops. Discontinuity. Okay, now an interval of increase or decrease. So an interval of increase or decrease come within the function's domain where the y values, where the y coordinates get larger or smaller as we move from left to right. Now, this will take a fair bit of practice for your mind to get comfortable with, but really all we're doing, it is relatively simple once you get there. All we're doing when we're checking an interval of increase or decrease, if we're checking to see if an interval is increasing or decreasing, then we can just draw a vertical line and we can pull it across. Right? So if I'm pulling this across my function from left to right, I ask myself if the y values of my function are increasing or decreasing. I can see, if I'm just looking at the line, my function is getting higher and higher on my line. So the y values are increasing, telling me that this has an interval of increase for its entire domain, actually, and that is from x equals 0 to x equals infinity. And in fact, I realize I'm jumping a little bit ahead here, but I see that happens to be one of our examples. So the radical function is increasing on its interval from 0 to infinity. Now, when we state an interval of increase or decrease, we can use interval notation to save ourselves some time. Now, using interval notation is relatively simple. It can sometimes look like an ordered pair, but it's not. Using interval notation, we always begin and end with a bracket, and we have a comma in the middle. On the left side, we write the left endpoint. In this case, it would be, the left endpoint where it begins would be 0, and the right endpoint would be infinity. So this is our interval notation that we could have used down here. In fact, let's use that. So from 0 to infinity. Now, the left endpoint always goes on the left, right? It always comes first. So your left endpoint must always be a number that is less than your right endpoint, because your right endpoint must be a larger x value than your left. Now, when we're choosing our brackets to go around for interval notation, then we're going to, at this point in the course, we're going to be using round brackets, but very soon we will be using square brackets. A square bracket would mean that the interval includes the endpoint. So this would mean that it would be increasing at 0 all the way up to infinity. If ever you have a positive or negative version of infinity, you must use a round bracket. In this case, though, it is only increasing to the right of 0, so we would use the round bracket like we have written under here. Now, let's take a look at our absolute value function. So our absolute value function, we'll put that into Desmos. And we see here, if we look from left to right, so let's try creating a vertical line that slides for us. There we are. Perfect. So this red line, if I move this from left to right, I can see that I'm decreasing from negative infinity. I'm decreasing all the way up until x equals 0. Right, so our x values are telling us where we're looking. The y values are what we're looking at. We're looking to see if the y values are increasing or decreasing. So from x equals infinity, from x equals negative infinity, the negative infinite distance of x, all the way up to 0, our absolute value function will be decreasing because it's going down. Now, once I hit 0, it starts going up. So there, our interval of decrease ends. So we would say that our interval of decrease for the absolute value function is from negative infinity to 0. Now, after 0, I can see that it's increasing, and it's going to increase forever. So the interval of increase will be from 0 to infinity. Next, we'll look at our cubic function. We'll turn off that absolute value function. We'll go to the cubic function. Okay, well, the cubic function has much more extreme values of y. But either way, we can look at this again from left to right. That's the key, because if I look at this from right to left, then it will tell me the opposite direction. It will tell me it's decreasing when it's actually increasing, or vice versa. So we always must look from left to right. So we look from left to right here. We're looking at the green function, at the green line, and we're seeing if it's going higher or lower along my vertical line. I can see that it's increasing. It's going higher and higher as I move my red line from left to right. So I can say that it's increasing. The only exception here would be right at x equals 0. At x equals 0, this green function is actually neither increasing nor decreasing. Okay, so here we have an interval of increase beginning at negative infinity. It begins, it's increasing, it's increasing, it's increasing, and then it stops. It does not include 0. And then we have another interval of increase from 0 all the way to infinity. So what we use here is a union symbol. So our cubic function is increasing on the interval from negative infinity to 0, and on the interval from 0 to positive infinity. Now, if we're going to to combine both of these intervals, then we say the union. Just this symbol here, it means on both of these intervals, but note the only point that's not included in these intervals is at x equals 0 itself. Okay, so we can push on forward for n behaviors. Here we're looking at the function. We're going to see the behavior of the function at extreme x values. So that means we're looking where our x values get very, very, very high, up to positive infinity, or very, very, very low, down to negative infinity. So we'll take a look here. The notation we're going to use, the notation that is common, is as x approaches. That's what the arrow stands for here. As x approaches positive infinity, then we'll state what y approaches as well. So here, we're working with our base quadratic function, right? F of x equals x squared. And we'll just do a quick sketch of that. We know what that looks like. It looks like something like this. Good. So we're going to take a look in x to see how y behaves, right? So x tells us where we're looking, y tells us what we're seeing. So if we zoom in here at extremely negative values for x, so as x approaches negative infinity, that's how we write that, then we'll say y approaches, and we'll see where it goes. So we'll take a look here at x, and here we're going to look, because we're approaching negative infinity, there's only one direction to approach that from, and that's from the right. So we're going to look from right to left now, which is different than the intervals before. From right to left, we're looking as x approaches negative infinity, y will approach positive infinity, right? Y is going higher and higher and higher and higher. So y approaches positive infinity. And then for our other end behavior, as x approaches positive infinity, y approaches, and let's take a look here. So we go in extreme values of x, right? And we're looking at our function in extreme values of x, extremely high values of x, and our y coordinate appears to get higher and higher and higher and higher. So y approaches positive infinity as well. There we are. Here are the end behaviors for f at x equals x squared. Now, after going through this example, we'll jump back into the activity. So there are more remaining functions that we're going to work with. And now that we've learned new characteristics, right, we've learned about asymptotes, we've learned about the continuity of functions, we've learned about intervals of increase and decrease, and we've learned about end behaviors. So we're going to fill in the remaining characteristics, we're going to leave type of symmetry alone for now. So we can jump into the handout. Sorry, here we are, into the handout, and you can see from these four functions that we already went over, we also have our new behaviors to take a look at here. So the continuity, you can double check my answers with your own understanding here. The increasing intervals, practice that. Try it out on your own and then compare your answers with mine. Same thing with the rest of the behavior here. You can pause the video, compare your own work. Pushing forward, and if it's blank, it's because it doesn't have any. So the linear, cubic, and radical functions do not have any decreasing intervals there. And we have four more functions. You can see how they're sketched down here. In particular, I want to bring your attention to the reciprocal and the exponential function. In these cases, we have asymptotes, right? Our asymptotes are sketched in with the dashed line. We see a vertical asymptote where x equals 0. And a horizontal asymptote where y equals 0. These are, again, sketched in already with a horizontal dashed line for the horizontal one, a vertical dashed line for a vertical one right here, and they're labeled. In order to properly have an asymptote on a sketch or on a graph, you must label it. So x equals 0, y equals 0. For the reciprocal function, there's only one asymptote. Right there, whoops. The reciprocal function only has a horizontal asymptote. You can double check this when you're going into Desmos and you're trying to see how it behaves. Again, it's sketched in with the dashed line and it's labeled. Those are the two important parts if you're going to sketch a function that has an asymptote. And we have our sinusoidal function. This one oscillates. That's what we say when it That's what we say when we mean it goes back and forth. So it goes up and down and up and down and up and down, and it will continue to do that forever and ever in both directions. That's why we have the arrows here and here. And our absolute value function, we've played with that a little bit already. Now you should have the know-how, so you can try and fill out the chart beneath for these four. Pause the video here while you're filling out that chart. And then you can compare your own work. You can pause here to compare. Hopefully there are no surprises. If there are, compare yours to mine and see if you can understand why the answer might be as it's displayed right here. And again, type of symmetry, we're not worrying about type of symmetry quite yet. We haven't gone over that in the lesson. Back to the lesson though. So we've sketched the remaining functions and we've filled in the characteristics, leaving type of symmetry blank. So, whoops, sorry about this. So here is a bit of a practice one. You can do this one on your own, trying to find the base functions that have the domain, all of the real numbers that have this certain range. You can practice that on your own. I'm not going to go over that in this video. Same thing with example 3, matching the functions with characteristics. These solutions will be posted on the Brightspace classroom, but I am not going to go over them in the video. We will jump into, though, a new definition. This is what we call an even function. So an even function talks about the symmetry of a function, and in fact, it talks about the symmetry of a function about a y-axis. So if a function is even, then it is symmetric about the y-axis. And that means if a function is even, then algebraically it will look like this, and graphically, this is the more important part here, graphically, our function will behave any activity, and I'll draw it. Ooh, that's going to be difficult for me to draw. Let's try this. Any activity that behaves on the right side of your y-axis will act like a mirror, if you will, or like a reflection here. So our reflection is going to happen about the y-axis. It's going to be symmetric about the y-axis. So our shape would be something like this if it were even, where you see I'm trying to follow the same behavior. So f at negative x, so let's say f at x is here, must equal f at negative x over on this side. Okay, and it must be true for all values on the function in order for the function to be an even function. Okay, now we can check algebraically, we can check to see if a function is even by calculating by evaluating f at negative x, right? So if we know, we're going to work again with this base quadratic function. If we know f at x, we can use that to calculate f at negative x. So since f at x equals x squared, then f at negative x, where we substitute in negative x for x, negative x squared, and negative x squared, I know that equals x squared, right? The negative would disappear because it's being squared in here. So since f at negative x equals x squared, and I know x squared, I'll switch to another color, I know x squared equals f at x, and really I should write that beneath. That means that f at negative x, where I just draw that, where I bring that down, f at negative x equals f at x. This is the definition. This is the definition of an even function. Definition. An algebraic definition. So that means, therefore, f at x equals x squared is even. Awesome. Then we'll take a look at odd symmetries. So odd symmetries are not symmetric about the y-axis, but they do have symmetry. An odd function is symmetric about the origin. So in this case, f at negative x, again, this is the definition. F at negative x equals negative f at x. Okay, well, what does that mean? If I know, and let's draw a similar, you know what, there we are. We'll draw a shape like this. This means that that f at negative x equals negative whatever f at x was. So if it equals negative whatever f at x was, then it's going to be the same thing, but on the other side of our x and y axes. So down here, it'll go in this direction. Oh, back there we are, where it has the same shape, the same general shape, except it's almost flipped here and flipped here, right? So it needs to be on the other side of the x-axis, but the distance away from the x-axis is going to be the same, but in the opposite direction as it was for on our positive versions of x. So positive x is over here, negative x is over on this side, right? So f at negative x, so that means something on this side, equals negative f at x, the version on that side. So we'll try it out. We'll test algebraically. We'll test to see if we can find a function that is symmetric that way. We'll use the cubic function, again, the base cubic function, our parent cubic function here. We're going to work with it. And in order to find it, we need to check to see if a function is odd. We need to find two things. We need to find what negative f at x equals, and we need to find f at negative x. So we'll start off with f at negative x. F at negative x equals negative x, where we're substituting in negative x for x, so negative x cubed. And we'll try that out. A negative number, all cubed, would just equal negative of the number cubed, right? Where the negative sign can come outside the brackets. So from here, we can say, okay, well, does that happen to equal negative f at x? Well, I know that f at x equals x cubed. So if I substitute this in down here, then I'm left with negative f at x. And this is, I'll bring this down, f at negative x. This is the definition of an odd function. So therefore, f at x equals x cubed is odd. Now, there are a number of practice problems here. We're going to go through the first two, and then I will leave you for practice the final four here. So we want to determine if the following functions have even symmetry, so we'll check to see if it's even, or we'll check to see if it's odd, and if it's neither, then we'll say it has no symmetry at all. Okay, so first we're working with a kind of linear function here. F at x equals 3x minus 2. We'll use the definition. When we're checking algebraically, if a function is even or odd, we need to use the definitions. So we'll go back up here to these algebraic definitions, and let's erase all the markings I put around them. So far, we're going to use this definition to see if it's even, and that definition to see if it's odd. So first, we check to see if it's even. If we're doing that, we need to calculate f at negative x. Okay, f at negative x equals 3, and then instead of writing x here, we're substituting in negative x minus 2. And then we'll simplify what's going on here. That equals, negative 3x minus 2. Okay, now our question is, does this equal, this part here, does this equal f at x? And a quick comparison tells us absolutely not, right? Our first term is negative in this case. It was positive for f at x. So herefore, we would say that this does not equal f at x. And our conclusion here is therefore it's not even. Now, just because it's not even does not mean it has odd symmetry, so we need to check as well to see if it has odd symmetry. Luckily, we've already calculated the first part, f at negative x. We've already calculated that here. Now we need to compare that to negative f at x. Okay, so we're going to compare f at negative x down here to negative f at x. So we'll say we'll find negative f at x here. Negative f at x equals negative, and then everything I see up here, right? So negative 3x minus 2. And that equals, if I distribute this, negative 3x plus 2. Now, we're asking ourselves, does this negative 3x plus 2, does this, which is my negative f at x, does this equal f at negative x? Because these are both sides of the definition here. Are they equal? No, they're not. One of them has a positive 2, the other has a negative 2. So we can say, therefore, this does not equal, and I know I'm running out of space, sorry about that. This does not equal f at negative x. therefore no symmetry. Good, and then we'll work with B here. We'll try it out. We'll check the symmetry here for this. Again, it's a linear function. So we'll find f at negative x, f at negative x here. Struggling to write this. F at negative x. So that's what we're finding. F at negative x equals 1 over 3 times negative x. And if I simplify that, that's negative 1 over 3x. And then we'll check, then we'll compare that to f at x. Does f at negative x equal f at x? Because if it does, that's the definition for our even function. I can see right away, one is negative, the other is positive, ergo they are not equal, so it does not equal f at x. Therefore, it's not even. Okay, then we'll check to see if it's odd. So checking to see if it's odd down here, we find negative f at x. And we compare that to our f at negative x, right? F at negative x is here. Negative f at x is there. Those are what we're comparing for an odd function. So negative f at x equals negative 1 over 3x. And I can see right here, these are equal. Right? They're absolutely equal. So I can write that equals f at negative x. Therefore, this is an odd function. It is a function that has odd symmetry. So you can practice that down below. Each time you need to calculate when you're finding, again, when you're checking to see if a function is even, then you're trying to find f at negative x, and you're comparing that to f at x. If you're checking to see if a function is odd, you're finding negative f at x, and you're comparing that to f at negative x as given by these definitions. Okay, so try it out for all of these problems down here. Again, they will be posted in their complete form on the Brightspace Classroom.